All right, he's been a member of the community for quite a while now. He's a co-founder of Tiger Beetle, one of Zig's most promising projects right now. He's the captain of concurrency. He's the prince of parallelism. King Butcher.
Okay. Quite an intro. Hello, can you hear me? Okay. So this talk is going to be themed on a game that Loris introduced to me a while back. Can tell it's probably Ultra Kill if you haven't noticed already. So let's get into it. So a little bit about me. I love I/O, love concurrency, but most of all, I love optimizations, and this is going to be all about that. Matt mentioned before, I work at Tiger Beetle. I'm mostly on the storage engine side of stuff, and I'm also on the Zig core team, which means I can just merge PRs. That's about it. So I barely do that even, but that's fine. So let's begin with the Prelude. So when you're thinking about parallelism, you have to actually know what it is before you have to get into it. So I would describe parallel as doing two things at the same time. So it's flipping two coins. And this is different from concurrency, which is doing two things, but not necessarily at the same time. So that's a good way to distinguish both of them. So in this talk, I'm mostly going to be talking about concurrency because the OS actually provides you parallelism for free if you just use their OS threads. And so you just explain the problem using OS threads, which is concurrency, and then you get the parallel part for free. So to get into it, you start with the temptation. So why would you use threads? Like, I assume clearly like 2 hands is better than 1. If you're doing tasks, you want to do it faster, right? Replace hands with developers, and that might not be such a good idea. And I'll explain what that means later. But you also might want to use it because you heard it from someone else. So there's like big projects that you hear that they start adding threads, and then like the performance like 3x's, 4x's, whatever. That can be misleading if you don't know how they did it, because they probably struggled to do that in some way or another. Or you want to do it to speed up existing code. This one is questionable. It can be done, but you should probably follow the steps in this guide to do it. So there's also cases where you don't want to use threads. So like the obvious one is that tasks rely on each other. So if you have 2 things, but one of them has to complete before the next one starts, then obviously you can't run them concurrently, so you can't use threads. Another, I guess one back, whatever. Another is if the entire system needs to change. So that means, like, take Python, for example. You already know, like, the global interpreter log, right? It's the famous solution where you can't add threads to Python because literally everything relies on it being single-threaded. So in that case, it's probably better to just design a completely new system rather than trying to hack on threads into Python, but I won't stop you. The other situation is if concurrency already exists. That way you probably don't even need to use threads at all. So like if you have non-blocking I/O, the kernel provides I/O that doesn't block threads for you, so you don't need to use multiple threads. You can just use one thread. Or if you use like SIMD stuff, that's like I/O, or not I/O, but it's compute done in parallel without threads. It's just the CPU does it for you. Or if you're like a GPU person, the GPU does it for you. So there's cases where you don't even need to use threads at all, but you can still do parallel stuff. And the last one is if single thread is actually just fast enough already. This is honestly the more common case, and I'll explain what that means in a bit. So like, let's say you're sorting 100 integers, right? It takes like 3-5 microseconds to sort 100 integers. So to wake up a thread, just waking it up is like 5 microseconds. So you can see how, like, if you're not even sorting up to 100 stuff, you shouldn't be using threads like at all, let alone spawning them, which takes like 5 times the amount of time. All right, so when would you actually want to use threads? So you just need more CPU time, right? Maybe you want to pump out more I/O, like if you're doing a ton of microservices, and you just wanted to make the most I/O throughput just to offset all your microservice overhead. Or you want to do more compute to offset all your crypto mining overhead. I don't mean to throw shade at all of these because the thing I work on Tiger Beetle is kind of both in some sense. So we do a lot of storage I/O, and we pretty much checksum everything we touch from network and storage. So we're kind of the worst of both worlds. So with our dilemma, we have a single-threaded event loop. So our being single-threaded is actually an advantage because everything is deterministic. I/O is deterministic because we can plug in our own I/O, we can do in-memory stuff, we can test a lot of stuff. It just helps for deterministic testing and fuzzing. And one of the problems we had was some parts of the Tiger Beetle stack was actually blocking the event loop, and this would limit our throughput or our performance. So this is what a trace looks like, or I guess a flame graph. So as you can see, there's a lot of different stuff happening in Tiger Beetle, but the big ones are here, and those are the checksum. So anytime we read data from the disk or the storage, or even I/O, we checksum all of it just to make sure everything's right so that we can detect faults. And just doing that over and over again adds up like a lot of CPU time. And if we don't interleave it with I/O, then I/O gets starved. So all that CPU time is blocking the event loop. Another thing that's blocking the event loop is the sorting of our in-memory structure. So how a database works is that we accumulate a bunch of stuff in memory, and then we sort it, and then we write it on disk, and then we use like some sort of lookup algorithm for that. The sorting of that accumulated in-memory structure is actually a big part of the CPU time. So this looks like a case where you can like plug in threads, like get performance increase. So we tried that. Well, I tried it, and it didn't really work out as intended. So there's the issue number if you want to go read the downfall of it. But basically, I tried to offload the sorting and the checksum to separate threads, and that actually helped, but it made the code a lot harder to reason about, especially for deterministic scheduling. So instead, we just switched to a faster hash to checksum. Like originally, we were just using like reference implementation for the checksum, which is kind of slow. And so we switched to like hardware-supported AES instructions, and that like completely removed it from the profile. So we didn't even need to add threads at all. Another thing is just to sort incrementally. So basically yield during the time we sort the in-memory structure. I was supposed to be working on that before I went to the talk, so I kind of paused it for this. Sorry, Jerron. Yeah. All right, on to the next chapter, indoctrination. So now you've gotten the mindset of it. Now we need to actually get you into writing threads, so hopefully you don't get out. So to prepare for writing threads, you first need a way to see if what you're actually doing is actually making a difference. Because if not, then you could be adding threads and it can also just make things slower. So one way of doing that is to profile your entire application. That just shows you the CPU hotspots and what you can actually move to threads if you even want to add them. And so, yeah, once you do that, I mean, you can start writing your own, but you should probably look at existing stuff first. That'll lead you to not make the mistakes that a lot of people make when they start writing threading stuff. So Zig currently has a thread pool that you can use. Please do not write your own, or if you do, let other people see it so they can show you what's wrong. There's also like other stuff that's not Zig related. So like your OS, if you're on Mac OS, you have lid dispatch. That's like its own threading queuing system that you can use. And if you're not even in the Zig sphere, there's also other tools. Like if you're in C++, there's Intel TBB. If you're in Rust, there's Rayon. So you don't have to always really start hacking on your own primitives when you want to add threads. So when you're adding threads, you need a mindset or a way to frame stuff so that you don't get disappointed when things don't go your way. So a good question to ask is, what are you willing to use? Or what are you willing to apply to the problem? Would you use SIMD for your problem? If not, then you probably shouldn't try to put threads, because that might be a bit more complicated. SIMD is just a good example because it requires you to think about the problem in a different, like, concurrent way, or grouping operations together way. Another way is, would you use an entirely different language for your problem? So that is the logo of a language called Futhark. It's for GPU programming. So that also requires you to think about the problem in a completely different way than how you do it serially. So if you're using threads, it's kind of in the middle. So you're still using the same language, but you still have to look at the language in a different way to solve your problem. So basically you have different rules. Some of them might be a bit confusing to people who like write serial code pretty often. So one of them is, it's better to duplicate work than to communicate with threads. That sounds bad for performance, but communication is really the killer of thread scalability, so it makes sense in this. There's just some different rules I have to keep track of that people don't really mention that often. But the main things that you should avoid is the 3 sins of threading. So the first one is spinning. You probably do this. It's like lying. You also probably do that. But it's not too consequential in the right settings, so like you can get a pass. The other one is dependencies. You can steal, but it's morally questionable sometimes when you do it. You should avoid it if possible. And then the last one is, I'll leave that to your imagination of how bad that is. But we'll start going through those. So, with spinning, how many of you have written code that looks something like this? Yeah, that's what I thought. All right, yeah, don't do that. You'll probably try something like this as well. This is just a way to tell the CPU, hey, I'm spinning, don't use as many resources. This is still bad, don't do this either. At least not unboundedly. Because you can pretty much hog up the entire thread quota for your thread. So when you're spinning on something that you're trying to check, the thing that's supposed to relieve that check to stop you spinning, you could be preventing that from being scheduled in the first place. So you're just like locking up time for no reason. Another thing you could have probably done, I'm kind of guilty of this too, is to replace the pause with the yield. So you yield the thread back to the scheduler. This may sound like a good idea, but it's actually pretty bad for different reasons. So maybe the thing you're trying to lead to is not on the same CPU core. So in yield, most implementations of yield only look at the current core they're on, because to reach to other cores, that's a pretty expensive check. And so they only look at the current core. So if your core is if your thread that you want to yield to is on a completely different core, then you'll just yield for no reason and check the scheduler for no reason and waste CPU time. Another problem with yield is that you could probably just yield to a completely unrelated thread. And so you just gave up CPU time for no reason, again. This is the worst of them all. And by your reaction, I can tell a lot of you already do it. So this it's good and it's bad, but for 2 different reasons. It's good for throughput. So if you add this in benchmarks, it might look like it got really, really fast. But what you actually did is you just reduced contention, pretty much. You just made it single-threaded, but scuffed, pretty much. So all the unlucky threads are sleeping while one of them is doing all the work, pretty much. So that's good if all you care about is throughput. But if you care about latency, like if one thread finishes and then the others are just waiting for like 50 milliseconds for no reason, there's not a reason for them to really do that. So to fix that, you should switch to something that's more like this, basically using events instead of spin loop. Like the main idea here is that you should use signaling, so wake up the thread that's waiting for something instead of having to continuously pull it, because that's always inefficient in pretty much almost every well, not every situation, unless you're like doing super low level driver USB stuff, but generally just do signaling instead of polling. So a way a signal is implemented is just through queues. So if you want to wait for something, you put your current task on a queue, and then when the thing finishes, then you schedule it again. So you can do this in your synchronization code. DOS does this with threads. It's pretty much queuing all the way down in the hardware stack. Even like the CPU cores do queues with each other for cache coherency. One thing to avoid when queuing is thundering herd. So this is when you wake up pretty much everything that was on the queue, and then they all like hammer the scheduler, and then they all race for the same thing. Some ways you can fix that is through chained waking. So you only wake up one, and then that one wakes up another, and that one wakes up another. So that way you avoid all the contention of them all waking up to like mess up on the same resource. The second sin, dependencies. So let's say you have 3 threads ready to go. They do work, and you put a lock on it. Why'd you do that? Don't do that. That just limits your concurrency by a lot. So generally, what you want to do is you want to avoid having things collect onto one shared resource. So one, run as many tasks as you can, just to increase the amount of available concurrency that you can achieve. And then to prevent stuff racing or blocking on each other, have like a race to register pattern. So they can all like do the same work, and then have them, only one of them register the results. That means they don't have to block on each other, trying to figure out who did trying to figure out who should do what part of the result. They can just all just do it together, and whoever's fastest wins. That's generally faster because they have less to communicate. This all just stems down to minimizing the critical section. So a critical section is just the small part of code where threads have to stop and get consensus on what's actually happening, really. So if you have you have them all race, right? And if all they have to do is just register the result, the amount of time they have to decide on the right value is just for the registration, not for the entire operation. So just minimize how much time is like spent on locking, pretty much. Also, avoid deferred handoffs. So this is kind of a tricky situation, but let's say you have a lock, right? And then you unlock it by passing it to another thread and telling them that, hey, they have the lock now. That's kind of bad because, well, it's good for fairness, yay, but it's bad for throughput because basically you just stop pretty much every other thread from acquiring that lock until that other thread that you gave it to wakes up. And that can be like forever because you don't control the scheduler. So you just limit the throughput that way. This is a bit more controversial, but you should probably try to stick to channels or queues instead of mutexes. Mutexes have a lot of like, you're doing the critical section things yourself, and that's easy to mess up. Channels make those sections really small. It's just send and receive, and then all your other code can just like run outside of that critical section. So this is kind of the same idea, just as a library form. Another thing that is technically a dependency is not using wait groups. So imagine you spawn like 10 threads, right? And then they all do their work, and then you join them all to wait for them all to complete. Instead of just joining all of them, because a join is a syscall and back, a syscall and back like 10 times. Instead, you can just have a counter. So each thread completes, they decrement the counter, and when it reaches 0, that's when it does a wake. And so the thread that spawned them only has to wait once, or do one syscall, instead of having to do n syscalls for all the operations to complete. This is a pretty common thing that a lot of people miss. This is a more esoteric one. There's a data structure called an event listener. It's better than a condition variable because it lets you wait for an arbitrary condition without having to lock a mutex. There's a library in Rust for it, and I think Dmitry Vyukov made the initial one back in like 2003-ish. But if you can, and if you're doing like lock-free stuff, then prefer those over condition variables. And the last part of dependencies is a bit more low level. So let's say you want to use a mutex, you kind of have to, channels are a bit too much overhead, so you want to use it. prefer an RW lock if you can. So an RW lock is kind of like a mutex, but it has two types of lockers, the readers and writers. Writers block everyone else until they complete. Readers, they only block writers, but they don't block other readers. So less blocking is better if you have a lot of reads. Also, if you have a lot of reads, you can just not have the readers block the writers at all. So there's a thing called read copy update. It's a bit tricky to implement, so it's kind of reserved for like really specific high performance cases. But basically, the readers just do their thing, and then there's only a single writer. And when the single writer switches out what the readers are using, and then waits for all the existing readers that were using that to complete. So the writer is the only one that blocks, and the readers can continue on their own. They don't have to ever block. So this is the final sin. So contention is the biggest killer of performance. So contention is when two things kind of intertwine with each other on the same shared resource. Having to resolve that collision kind of messes up a lot. So this is the main killer of threads. Not the mutex stuff, although that can be a big killer, but underneath, it's just the atomic operations just colliding with each other and slowing each other down. So let's say you have a basic lock-free incrementation thing, right? This is how you normally implement it. It's a CAS loop, it loads the value, and then keeps trying to increment it. If it's the first one to increment, then it's done. If it's not, it gets a new value and tries again. For something simple like this, you could try to just make it hardware encoded. So most CPUs have something to represent like basic atomic instructions, but they have their own like collision resolution algorithm to make contention faster. If you can't do that though, like if your operation is too complex for it to have like a hardware representation, then what I recommend instead is you have some sort of like back-off mechanism. This is honestly more prevalent in distributed computing, but less so in local computing for some reason. Like if you have like AWS API or whatever, and it gets overloaded, the recommendation is to add like a back-off, like a timeout, like wait 5 seconds and try again, wait 10 seconds, try again, something like that. And that's like the recommended solution, but apparently it's not for threads. And this helps like a lot. I have a GIST showing the throughput difference. It's like 2x if you don't do this versus if you have the normal event loop approach or retry approach. Let's see a different example. So let's say you have a lock-free queue, and you try to lock it, and you push stuff, and you try to lock it, and you remove stuff. Pretty basic. What you can improve on this is that every time a push or a pop, well, every time a pop happens and it's empty, you just still have to lock the mutex. So in this case, what you can do is just check the length before you try to lock the mutex. Because reading doesn't have to go through all the contention resolution stuff. So if you can read without having to write, which is a mutex lock is a write, then your pop on empty values can be really quick. So that just involves like adding a store to anytime you update the array inside the lock. You can go a bit further, and you can only update the count if you did a modification. So like if pop didn't return anything, then you don't update the count, and that doesn't make the load above have to go through the collision stuff like last time. Another way to avoid contention is to just split stuff up, basically. So one example of this is Linux Vutex. It's just a way to park threads. What it does is it has a table of wait queues, pretty much. And the way it makes it so that one address, or thread waiting on one address doesn't have to contend with a thread waiting on another, is just to put them in separate queues. And that is a way to reduce contention because they're no longer on a shared resource, pretty much. A practical example of this is dash map. If you're in the Rust space, this is basically a concurrent hash map. And all it is underneath is just a hash map, but a lot of them, yeah. It's pretty good. Another thing you can do is put things on separate cache lines. If things don't necessarily contend, but aren't in the same memory space close together, they'll still end up being contended underneath. So you can avoid that by like just spacing them out in memory so they don't have to deal with all the hardware contention stuff. Also, another way is to just batch stuff before contending. So instead of doing a push and locking the mutex, doing a push, locking the mutex, push like 5 things, then lock the mutex. So you don't have to do that every time. Allocators do this. Run queues do this. I don't feel like explaining those. And the last one, corruption. So I was gonna get into lock-free programming, but I don't think I have enough time for that. So I'm gonna pull a VLang, and now it's just work in progress. So to wrap it up, basically, optimize single-threaded first. You don't have to pull out threads immediately. Generally, what you want to do is just make single-threaded fast before you even consider threads at all. Have a way to measure stuff, because adding threads can slow things down if you introduce dependencies, introduce contention, introduce spinning. So have a way to make sure that adding threads is doing what you want it to do. Try existing solutions first. All of these problems are generally, well, most of the time, people consider these problems when they publish libraries. So you can just use libraries if you want to avoid having to deal with all this. And then remember the 4 pieces to avoid all of this. Accumulate. So the more tasks, the better. Higher the concurrency. Remember, you're in the business of task spawning. Satiate. Make sure the tasks are nice and full, nice and fat, not too big, because then you don't take advantage of CPU cores. Not too small, because then you start hitting contention. Cut off all forms of communication for the tasks, just to make sure that they don't have to contend with each other and they keep doing the work that you actually want them to do. And then finally, consolidate, ask for help, because I didn't learn all this on my own. Most of what I know about threading, about concurrency, about I/O is just from other people. I just go on random discords, work on projects. I send them like broken atomic algorithms, and then they criticize me for it, and that's how I learn. Yeah, these are not steps for a cult, by the way. And that's it. Yeah, that slide took me like 5 hours to make, so you're welcome.
Hey, any questions?
Great talk. One question I have is, often when you're dealing with how to distribute your workload across threads, there's a lot of different challenges that come into play there. And you were mentioning that sometimes it's good to just duplicate work if it means that you're going to reduce communication, right?
Yeah.
How do you, there's a lot of ways to do this, I'm sure, but how would you recommend making sure that those threads start in different places? Would you just distribute the data and give them a different index to start at, or how would you do that?
It depends on the type of work. So the type of stuff I do is mostly like super low-level atomic data structures. In that case, it's better for them to compute a large result that all threads have to do and just have them race. So in that case, you're just working on the same thing. They're not actually working on separate parts of the same problem. It's just the same thing, and whichever wins.
Thank you.
Great presentation, as always. Thank you. There was one note on mutex versus RW lock. So I actually had this. At least in Go, the way it's implemented, RW lock, the constant overhead is much higher than just using the mutex. So in my case, I think I found that if there are less than 10 readers or so and the critical section is low, it still makes more sense to use the lock. So if the critical section is really small, it actually, unless you have like dozens or hundreds of readers, then it's still better to use something that uses lower overhead.
Were you using POSIX locks? by chance?
I was using whatever golang.lock, the Golang's mutex. I'm not sure what's behind it. I don't think it's a POSIX lock.
So when it comes to like synchronization primitives, there's like good and there's bad ones. Generally, the system ones are considered bad for most cases. The reason I say use RW lock of your mutex is that you can make an RW lock as fast as a mutex. Like in Windows, their RW lock is their mutex pretty much. So in your case, you might just be using a slow RW lock. That's just my intuition.
This is like specific to whatever Go standard library has. And I seem to recall the RW lock has a spin lock inside, so that may be the case.
Oh no.
And I also know that Matt has a question, so don't forget about it. Or should I ask the question, Matt?
You get it.
I get it. Okay, so there was a problem in the previous presentation, as we all recall, async. Can we get rid of it?
You're like the second person. You can, but you're gonna replace it with something even worse. Someone's gonna find a way to do async that is gonna be very hacky, whether it's through like stackful coroutines or whether it's through like some sort of Zig build system thing. Like honestly, in Tiger Beetle, right? A lot of our code is asynchronous in nature, and so we don't have async yet because it's buggy and we're probably gonna update to stage 2 later on. So in the meantime, all we do is just like intrusive nodes and then callbacks and callbacks and callbacks and callbacks, and it turns like something that could have been async into like 100 lines, 200 lines. And honestly, it would have been better to just use async. So if you want to get rid of it, you're going to make a lot of people angry.
Thank you for the mature answer, as always.
Yeah.
Any more questions?
What was secret number 4 that we missed?
Can you say that again?
What was secret number 4 that we missed?
The number, I'll leave that to later. It's a secret, obviously.
Okay. Anyone else? All right. Oh, Loris.
Thank you, King, as usual, also. Great presentation. While you're here, can you also do the audience a second favor? Like, I think your talk was already a big favor to everybody. The second one would be, can you pitch to them UltraKill?
Okay, so Loris introduced, I don't know how this is related, but Loris introduced me to the game like 2 weeks ago at random. I saw gameplay of it. It seemed kind of boring because I'm a Quake guy, and I tried it out. It was like pretty cool. The lore is interesting. Community is interesting. That's one way to put it. But the game is really nice. It's a fast first-person shooter. Has some really deep lore. It's about ascending into hell and all the levels associated with that. But it has a speed running system where you can record time and you can like get style meter. So what that P means is that you had a perfect score in time, so you completed it fast. You had I replaced jokes with kills, but you had a perfect kill rate, and then you also had a perfect style meter. So the game records your style, basically how you execute kills. So like if you're switching weapons, if you're jumping around, that's like your style. So a P rating is like the highest rating you can get for all three. And that's what that means. Ultra kill, yeah.
Any more questions? All right, let's have another 15-minute break.
Okay.
Okay, King, is almost your time to give a talk. This is your second talk, right? As of Recon Lab.
Yeah, that's my second talk. I did the first one 2022 in Italy, I think.
That was a pretty good talk. Is this one going to be better?
Hopefully, there's going to be a pretty cool thing at the end, so might as well watch through the end.
Well, looking forward.
Should we remove async from the language?
I'll let you think about that again and ask others. That's probably not something you should bring up here with people who love async.
I'm going to rephrase what he just said. We're going to beat you up. Okay.